Okay, everyone, I will start shortly. Please write your name in the chat area so that I can know that you were here, and we'll pick it up where we left off. We were talking about continuity, specifically uniform continuity, how this notion of uniform continuity is different from our regular continuity. So first of all, uniform continuity is about being uniform continuous on a set. And the important difference is that the delta that we pick, so there's an epsilon, and that delta works for every pair of points in the domain A. So it doesn't matter which two we pick. If they are within delta, then their images will be within epsilon. And we saw that many functions happen to be continuous. For example, x squared. Let me turn back to the page, and we saw that the function x squared is continuous in its domain. So last time, f of x equals x squared is continuous on the entire set of real numbers, but it is not uniformly continuous on the real numbers. However, we can make it uniformly continuous, and that's the last thing we saw, if we consider a smaller domain, right? And by a smaller, I mean bounded, right? So, however, f of x equals x squared is uniformly continuous on, say, the set negative 100 to 100, and this big interval. You can make it 1,000 or 10,000, doesn't really matter. As long as it is bounded, the answer will be uniformly continuous. So what is it then that makes something how can we have an equivalency here? And we also saw that uniformly continuous, so f uniformly continuous on A implies, of course, that f is continuous on A. So it's a stronger statement. But the opposite arrow doesn't work. So this one is good. Going backwards, going in this direction, not good. However, if we add a hypothesis to A, then this could be an if and only if. So, however, if A is compact, that's the result we announced last time, then we have if and only if, right? Then it's the same. Then you can talk about continuity, or you can talk about uniform continuity. You get exactly the same thing, right? So that's the next thing we're going to see. And in the book, this is theorem 4.4.7, right here. So theorem 4.4.7. And it says uniform continuity on compact sets. And what it says is a function that is continuous on a compact set K is uniformly continuous on K, right? So we have the arrow coming backwards, the arrow that goes from continuous to uniformly continuous, okay? So that's the first thing we're gonna do today. We're gonna prove this statement. And actually, I wanted to, the proof that is in the book is very beautiful, you know, very terse and straightforward proof, short, even elegant, you can call it even, but that sort of hides what's going on. Why is it that we can, where is the fact that compactness makes it work? So I'm gonna do two proofs, one like the one you have in the book, but also another one. Actually, that other proof is you're supposedly asked to do it as part of exercise 14, 4.414. So in a sense, I'm gonna be doing exercise 4.414. Okay, so proof number one, proof one, and this will be like exercise 4.4.14. Okay, so for this proof, we are going to use the equivalence of compact as a set where every open cover has a finite subcover. That's the property we're going to use. Okay, so let's do it. So what do we have? We have a function continuous on a compact set K. So assume f from K to R is continuous and K is compact. All right. Then I want to show uniform continuity, right? So for uniform continuity, what we really need is that if we pick two points in K that are, so we fix an epsilon first, and then we need to find a delta such that whenever 2 points in K are closer than delta, then their images will be closer than epsilon, right? Maybe I can write it here. Let's write it as a box of what we want. So we want for every epsilon to find a delta such that if x minus y are within delta, then f of x minus f of y are within epsilon. That's what we want. And presumably we have to use both that f is continuous and that k is compact, right? Because we know this is not going to work. We already have an example where what we want is not true if k is unbounded, right? If k is the entire set of real numbers and f is something as simple as x squared, then it doesn't work. So we better use our assumptions. So let's start by writing down what is the meaning of being continuous. And here is what it means, right? So we pick an epsilon. So first, let epsilon greater than 0 be arbitrary. We pick an arbitrary epsilon, and then because f is continuous on K, then this happens. Then for every x in K, there is some delta, and I'm calling it delta x because this delta may be different for different x's. There is some delta x greater than 0, such that what? Well, if y minus x is less than delta x, then f of y minus f of x is less than epsilon. So this is great. This is like we want. The problem is that we have different deltas, right? Different deltas for different x's, right? So this delta may depend on epsilon, but it also may depend on x. And that's why I'm calling it delta x, so that you realize that this delta, it depends on epsilon, but may also depend on x. So and what we want is something like this. You can see it in the green box over here. We want something like this, but when this delta does not depend on x, right? We want a delta that works for all of them. Okay, so what are we to do? Well, we want to use compactness, the compactness property, and specifically we want to use the open cover property, and so that then we can extract a finite subcover. And here, the harder part is to think what open cover should we consider? And this is exactly what we're going to be using, these delta x's. So what you should realize now is that now every point in K has a delta, right? So in other words, it's like you can ask yourselves the following question. So what are the points that can work with X? And the points that work with X are the points that are on this delta neighborhood around X. So that's the open cover we're gonna consider. So consider the open cover. The open cover V. And just to give myself a little bit of reading room, I'm gonna make these neighborhoods a little smaller. So I'm halving the delta. I'm making it delta over 2. So the radius of the neighborhood is delta over 2, and we're doing that for every point in K, right? And this is this open cover. This is certainly an open cover of K, right? Because we have 1 point uh, for every element in K. We have one of these open sets. So it's a gigantic cover, right? It has an infinite number of elements, probably uncountable, lots and lots of them. And it is an open cover because every element in K is at least the center of one of these guys. And maybe it belongs to even more of these neighborhoods, but at least is the center of one of these. Okay? So that's the first part that we need. And then we're going to use the fact that K is compact. And what we know about open covers with compact sets is that then we can extract a finite subcover. So here we go. Because K is compact, then there is a finite subcover. And here it is. I'm going to write it here, B delta x1 delta x2 over 2 dot 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 and delta xn center of xn, right? So there's xn of these guys. Okay, so that's fantastic because now we're gonna find a way to pick that delta that works for all of them. And in case you were guessing it already, what the delta that we think is gonna work for all of these guys is precisely the minimum of all of these, right? So now we have finitely many of them, so we can consider the minimum of them, and that's how we're gonna proceed. So we're gonna make delta the minimum of all of these little ones, okay? And we claim that this one works. So all we need to do now is show that this delta is going to be the one that gives us the property we need. All right. So let's try to do that. So suppose that x and y are elements in K such that x minus y is less than delta. This delta, the delta we just created. All right. Okay. So what's the story? Well, the story is that, well, X must be, see, these open sets over here, these neighborhoods cover the entire K, right? This is a cover of K. So, and this X is one element in K. So that means X must belong to one of these. So because write it like this, b delta x1 over 2 x1, b delta x2 over 2 center of x2, etc. is a cover of K. Then there is some I between 1 and n such that, well, such that x belongs to one of these guys, right? So X must belong to one of these because this is a cover. That's what I'm saying, right? Nothing fancy here. Okay, but now because it satisfies this property, this means actually the following, right? An equivalent way of stating this is that the distance from X to Xi is less than delta Xi over 2. Try this again, delta Xi over 2, like this. So that's the meaning of that. Okay, and then here's what I want to do now. My claim is that Y, the other point, this other point Y, it's also in this one. It's also in here, right? Well, actually not in here, but in the one that's twice as big. Okay, and here's how we can argue that. It's simply a triangle inequality type of thing. So what I want to now convince you is that Y and Xi are also close. So I want to look at this distance, the distance from Y to Xi, right? And as usual, we'll do the classical trick of using an intermediary, in this case, X. So we subtract X and add X, use triangle inequality. Right? And then what do we know here? Well, we know this one is less than delta, right? It's right here on top. And this, we know this one is less than delta Xi over 2. But what was delta? Let me go up a little bit. Well, delta was the minimum of these numbers. So in particular, delta is smaller than delta Xi over 2. So this is smaller than delta Xi over 2 plus delta Xi over 2. Put them together, you get delta Xi. All right? So what did we find? We find that Y and Xi are also close. Now here's the important thing. The important thing is that now both X and Y, both Xi and Yi are within within delta of delta Xi of Xi, right? So let me just write it here. This is the important part. Notice that both X and Y satisfy X minus Xi less than delta Xi and Y minus Xi less than delta Xi, right? I mean, I know that for X is even smaller than that. It's delta over 2, but delta over 2 also works here, right? So then we go back to where delta Xi came from. Remember, delta Xi is the delta that makes the Xi work for continuity. So let's go back, right here. So at the very beginning of our proof, we said for every X, we were gonna look at delta X. And so change X for Xi right now. And what it says is if Y is within delta Xi of Xi, then their images are within, I put epsilon over 2, by the way. Before, when I wrote it initially, it said epsilon only, but I need a little bit of breathing room too. So I've forgotten that I had to put epsilon over 2, all right? So I put epsilon over 2 when this was off the screen, but I need epsilon over 2 here so I can have a little bit of breathing room, all right? So we're gonna use this now, right? So it's continuity. So by continuity, we go back here. By continuity, the previous property, the one I just showed you, it follows that follows that f of x minus f of xi are less than epsilon over 2, and f of y minus f of xi are less than epsilon over 2. And from here, I hope you can see the ending of the proof, right? So what is it that we showed? We showed that f of x and f of xi are close, and f of y and f of xi are also close. And if we put those together, we can then show that f of x and f of y are also close, right? So all we need to do now, so finally, we do f of x minus f of y. And what we do is we use f of xi as the middleman. Triangle inequality. And each one of these is less than epsilon over 2. Therefore, this one is less than epsilon. And that's the end of the proof, right? So we started with an arbitrary delta. We pick arbitrary points x and y. And we showed that the images of those points are if x and y are close to each other, if x and y are less than delta, then the image of those points are within epsilon, right? So this shows that f is uniformly continuous on K. Reinforce that, because f is uniformly continuous on K. All right? Questions? It's an important proof, this one, especially because it's not in the book, right? Yeah, remember, this is one of the exercises, so you can't really go back and read it from the book because it's not there. But it is a proof that shows you where the delta comes from, right? So the delta that makes it all work came from using the minimum of the open finite subcover, right? Now, it's still a little bit mysterious because when we know the definition of compact, we don't know how to find that finite open subcover, right? We just know it exists. But here at least you get to see how is it that one delta can work for all the points, right? Because essentially we have finitely many deltas that work, and then the only thing you need to do is pick the smallest of all of them. That's essentially the gist of the proof. Okay? Questions? Okay, let me go back and we'll try now the second proof. It's a shorter one. So let me roll back the statement. So here's our statement. And we'll do proof number 2. And this is the one that's in the book. Okay, so this is a proof by contradiction. So we're going to use this property that we saw last time of not being uniformly continuous. Let me go back to the book and remind you about that one. So specifically, we want to use this one, theorem 4.4.5, one that I'm highlighting. Let's just highlight the name. And what it says is that a function is not uniformly continuous if we can find some epsilon 0, some separation distance, and two sequences that have this property. The sequences get closer to each other, right? The way you can write that is that the difference xn minus 1 yn approaches 0. But their images are separated. They're always epsilon 0 apart. Okay, so that's what we want to use. So we're gonna assume f is not uniformly continuous. So we start the proof the same way. We suppose that f is a function from k to the real numbers, such that f is continuous, but we assume it's not uniformly continuous. Okay, so let me go back to the page. So we suppose that f from k to r is continuous, and k is compact. That part we start the same. Then, by contradiction, suppose that f is not uniformly continuous. So then we can use the statement that I just showed you from the book, right? What is the meaning of that? It means there are two sequences. Yes, there are two sequences, xn and yn, both subsets of k, such that there are two sequences and there is an epsilon greater than 0. An epsilon 0 greater than 0, such that this happens. And the sequences get close to each other, but they are separated when you apply the function. All right? So that's, we're assuming by contradiction that this happens. And we know this is equivalent to not being uniformly continuous. So now we need to get a contradiction, right? So we need to hopefully get something that is not right. And the way we're going to do it is we're going to see what happens when we with these two sequences, right? Specifically, we're going to start with the sequence, one of them. We're going to pick xn. And we know k, we need to use that k is compact. If we don't use that k is compact, it's not going to work. So what do we know about sequences on compact domains, right? What do we know about a sequence in a compact set? What's the definition?
Closed and bounded?
Yes, so K is closed and bounded, but what do we know about sequences in a compact set? Yes, Petros wrote, they have a convergent subsequence. Exactly, that's what we want, right? So because K is compact, there is a subsequence X and K such that it's convergent, say to X, right? We have a convergent subsequence, all right? And then we're gonna use that convergent subsequence and figure out what's going to happen with. So let's look at the corresponding sequence with the y's, right? So consider y and k. So that's the same sub-indices. So if this subsequence was, I don't know, you pick the, for example, the, let's make it simple, the even terms. So imagine that this subsequence was x2, x4, x6, x8, etc. Then here we're considering y2, y4, y6, y8, etc. So the same sub-indices. So consider these sequences, this sequence, right? So note that what happens when we try to do the limit of this one? Well, not clear, but what if I write it like this? Y minus x plus x. Well, that's obviously the same, right? But what is better is that we know these two limits exist when I separate it. So I can use the algebraic limit theorem because both of these limits exist. This one that I'm writing and this other one. right? These two limits exist. This one exists right here because the difference goes to 0. And this one exists because we wrote it right here. It's convergent and approaches x. So more, this is 0, and this is x, right? So that's awesome. So that means this sequence also converges to x. Okay, we're almost done. All we need to do is look at the function. What happens to the function? So finally, by continuity at x, the following happens, right? What is going to be the limit of f of x and k? Well, because f is continuous, this has to be f of x, correct? But that's if you use the x's. What if you use the y's? Well, the same thing, right? Because the y's also approach x. So these two guys both go to f of x, right? But then I got something weird because then what is this limit if you look at the difference? If you look at this difference, well, this would be 0 minus 0, right? And that's a contradiction. Why is it a contradiction? Because we're saying that these two numbers get closer, as close as you want, right? The limit of this is 0. This directly contradicts this statement over here, that our sequences xn and yn were separated. Remember that? They're separated. And how can they be separated if they are going to 0, if their difference is going to 0? So that is a contradiction. Which is a contradiction to the fact that f of x and k minus f of y and k was supposed to be bigger than epsilon squared. Right? Okay, so that's the end of my second proof, right? So we got a contradiction. That means our assumption of not being uniformly continuous was wrong. So that means our function is actually, it is indeed uniformly continuous. All right? Yes, Ashot, question.
Yeah, I was just curious if the line where it says limit of f of x and k equals 0 minus 0, is it supposed to be fx minus fx instead of 0 minus 0 there?
Right here?
Yeah, because it equals fx, so I was thinking maybe it's supposed to be fx minus
Yes,
fx.
thank you. You're right about that.
Thank you.
Yeah, fx fx. Yes, yeah, both of them are equal to f. They both approach f of x. Yes, thank you.
Of course, thank you.
Good. All right. So this is the end of this section 4.4. A very important. So I opened up the wiki earlier this morning. One important exercise that all of you should try is number 11, which characterizes continuity in a different way using open sets. So very, very important that you guys check that out. It was included, it's an if and only if statement, and I can tell you that last year we used it. It appeared in both, I think, one part in the final exam and another part in one of our midterm exams. So take a look at problem 11. I consider it important, very, very important. All right. And so we'll now move on to the next section. The next section is a smaller one, 4.5. It's only, I think, 4 pages long in our book, but it's important nevertheless. And it's one of those things that one of those results that you sort of take for granted. And many people did, including Euler and Gauss, right? Really important mathematicians from long time ago, because we still didn't have the way to set up mathematics in a way that everything was made precise from an axiomatic point of view. So statements like the one I'm going to show you were thought to be obviously true. And this is what I'm talking about. So we're looking at the intermediate value theorem, right? The intermediate value theorem, you all know it from calculus. We mention it all the time, right? Essentially, what it says is that if you have a continuous function, then you have to go through any of the intermediate values, right? I'll show you a picture in just a moment. So let's read the statement. It says, if you have a function from a closed interval to the real numbers and it's continuous, and well, either one of two things can happen: f of a less than f of b, or f of a bigger than f of b. So let's go with the first one. If f of a is less than f of b, then there is some point in between, such that there is some point c, so that you achieve L when you look at the function for any L between f of a and f of b. All right, let me make a picture. I think that will clarify the statement in a better way. So this is a statement about continuous functions on a closed interval AB. So here's my my axis, and I'm gonna draw some function here, continuous. Maybe it's like this, or now let's make it a bit more interesting. Let's say that it goes up and down, maybe like this. And this is what it says. It says, here's f of a, and here's f of b. You can pick any number in between, right? You can pick any L right here. Doesn't need to be in the middle, right in the middle. In fact, let me move it a little bit. Maybe it's closer over here. You can pick this L, and what it says is the following: if your function is continuous and you have to go from here to here, right? Then no matter how you draw it, you have to cross this line L, right? That's what it says. To go from here to here, you need to, at some point, cross the line L. Okay? And let me just okay. Like I was saying, so the intermediate value property says that if you, it's sort of clear, right? It's precisely that property of going from one point to another and not lifting the pencil from the paper, right? How can I do it? If you don't allow me to lift the pencil from the paper, I cannot cross this line, then I won't be able to go to this point. That's essentially it, right? So it seems like a very, very simple statement, but it does require a proof. And we're going to give two proofs of that as well today, since it's such a smaller section and we have the time. We're going to present two proofs. Okay, so let's write the statement. So here's the theorem we want to show. It's theorem 4.5.1, the intermediate value theorem. And this is what it says. It says, let f be from AB to the reals continuous if L is a real number satisfying f of A less than L less than f of B, or f of B less than L less than f of A. So this only says we don't know if f of a is bigger than f of b or if f of b is bigger than f of a. So we're considering both possibilities. Then there is c in the open interval ab such that f of c equals L. Good. So like I was telling you, we're gonna do two proofs. Let's start with proof number one. This one is sort of well, both of them actually, in a certain sense, tell you how to find the C. Okay. So here is the first one. This one uses the properties of supremum, the property of the supremum, or infimum if you want. Okay. So here is the first one we're going to do. So first, we're going to assume the case where f of a is less than f of b. The other one is symmetric, right? It can be done in a similar way. And so we're going to assume this is the case. And here's how we're going to do it. We're going to create this set, the set S. And this will be the x's that are below L. All right? Okay. Now, is this could this be an empty set? That's question number one. Could this be an empty set? And the answer is no. Why not? Because look here, right here on top. We know that f of a is less than L. So at least a belongs to S, right? So let's write it here. Note that a belongs to S. So S is not empty, right? So it's not an empty set. Because it's not empty and it's bounded, right? How do I know it's bounded? Well, because it's inside a bounded interval, right? Also, S is clearly bounded by bounded above is what I care about, bounded above by B, right? Because S is a subset of the closed interval AB. So it's non-empty and bounded. It must have a supremum. So let's define the supremum. And we're going to call it C. Let C equal the supremum of S. And that's it. That's the one that I think this is the one that's going to have our property. This is the one that is going to be f of c equal to L. And then the only thing is that to prove that, we need to do it in an indirect way. We need to show what happens when f of c is less than L is impossible. And we need to show that f of c greater than L is also impossible. So if it is not less and it is not greater, then it has to be equal. That's what we're going to be doing now. Okay? So first, we're going to assume, so case one. Suppose that f of c is less than L, right? What if that happens? Well, if that happens, we need to use continuity at some point, right? So we need to use the fact that the function is continuous at c, right? The function is continuous at c. So I'm gonna use a specific epsilon, and here the epsilon that I want to use is this distance from L to f of c. So because f of c is less than L, there has to be some distance between these two numbers, and that's what I'm going to use. So let epsilon be L minus f of c, all right? Which is positive, correct? So using this epsilon, by continuity at C, there is delta greater than 0 such that what? Such that if x minus c is less than delta, then f of x minus f of c is less than epsilon. right? Now, let's rewrite what this means. Well, this means negative epsilon is less than f of x minus f of c, which is less than epsilon, correct? And here the important thing is, what is epsilon? Well, epsilon is right here, right? What is epsilon is L minus f of c. So from this inequality, if you add f of c to both sides, what you get is that f of x is less than L. All right? So look what we just found. Let's maybe time to draw a little bit of a picture here. Let me get a new piece of paper and let's draw a picture here of our situation. What is our situation? Well, we have C. Well, let me draw. Here's A and here's B, and somewhere in there is C, right? And then we said we're using as our epsilon L minus f of C. And here, this is what we have. It says we found a delta, and with this delta, what it says is if you pick numbers that are within this delta, so if I go delta this way or delta the other way, so points in here, when I apply the function, so all these points in here, when I apply the function, when I apply f, we get less than L, right? Okay. So in particular, if I go delta plus 2, right? If I pick a point that is delta plus 2, that number will still be bigger than C, right? So in particular, C plus delta over 2 satisfies f of C plus delta over 2 less than L, right? So if I pick some point to the right, that's the important thing. I have to pick a point to the right of C, okay? If I pick a point to the right of C and I pick this one, then it satisfies this. Well, that's a problem, you see. Why is this a problem? Let's remember what C was. What was C to begin with? Let's go back. Right here. Here's the definition of C. C was the supremum of S, right? C was the supremum of the numbers that are less than L when you apply the function. Well, looking here, this number, when we apply the function, it gives me less than L, right? So this number belongs to S. C plus delta over 2 belongs to S. Well, but that's not right, because how can a number that belongs to S be bigger than the supremum? Right? This is a contradiction because C plus delta 2 is bigger than C, which was the supremum. Okay? So we got a contradiction. That means case 1 doesn't happen. Okay? All right. So case 1 doesn't happen. So what is the, let's go back. So here's case 1. Case 1 was if f of C is less than L. So now let's go case 2. Case 2, suppose that, I'll show it in just a moment, f of C is bigger than L, right? Okay, so this didn't happen. Now let's suppose that is the other way around, that f of C is greater than L. And what are we gonna do? Well, a similar thing, right? So we're gonna pick as our epsilon, the distance between these two. So let epsilon be f of C minus L. Then by continuity of the function at C, there is some delta such that if x minus C is less than delta, then f of x minus f of C is less than epsilon. Same as before, right? And same as before, we're going to rewrite what this means. So this means that f of x minus f of c is between negative epsilon and epsilon. And in here, this time around, we're going to use the left inequality. So we're going to plug these in here, right? And this is going to give us that negative f of c plus L is less than f of x minus f of c. The negative f of c's go away. And what this means is that L is less than f of x. So the f's are also bigger than L, right? Same as before, we got the same thing, right? If I do the same picture, so well, before they were all less than L, now they're all greater than L. Okay, so time to do our picture again. So what's our situation? Here's A, here's B, somewhere there is C, and we got a little neighborhood, delta neighborhood, where everyone in here satisfies that f of x is bigger than L, right? That's our situation. And why is this bad? Well, this is bad because what it means is that all the numbers that are to the left this time, so all these numbers to the left are not in S, right? So let's go back to our definition of S. Let me put it on the screen. Here was our definition of the set S. So the set S are the numbers such that the function is less than or equal to L, right? So what we found out here is that none of these numbers, right? All of these numbers are greater than L. So none of these numbers belong to X. None of these belong to S, right? Okay, but if none of them belong to S, then how come C is the supremum, right? C cannot be the supremum of S if you can find some smaller numbers that could work too, right? So if none of these numbers belong to S, then this means that C minus delta, the C minus delta, if I pick this point on the left, C minus delta is an upper bound of S, right? Because the numbers that are less than L are all on the left, right? See, C was an upper bound because it was the supremum. So that means everyone was to the left of C. Everyone was from here. All the elements of S were from here to the left. But now these guys are not in S. So then that means now that everyone in S is to the left from C minus delta. So C minus delta is an upper bound, and that's a contradiction. This is a contradiction because C was supposed to be the least upper bound, right? So we got a contradiction in here as well. So from both case 1 and case 2, what is now our situation? F of C is not less than L, is not greater than L. Then the only possible remaining choice is that F of C is actually equal to L. So from cases 1 and 2, follows that F of C is not less than L, F of C is not greater than L, thus F of C equals L. And that's the end of the proof, right? We found the point such that when we apply the function, we get exactly the number the intermediate value that we wanted, the value L. Okay? Questions about this proof before we move on to the second proof? Okay, let's do the second proof. This second proof, I kind of like it because it's algorithmic in a certain sense. So it provides you with a practical way to find out the actual C, right? So again, let's suppose that f of A is less than L, less than f of B. All right. And here's what we're gonna do this time. We're gonna construct some intervals. So we're gonna start with our big interval AB is gonna be I0. So let I sub 0 be the interval AB. And L will be B minus A. So that's going to be the length of the interval I0. And then we're going to consider the midpoint of that interval. And that midpoint, we're going to call it Z. Is it Z or C? C, yes. Consider the midpoint. I'll do a picture over here. So here's A, here's B, and this point C is the midpoint. All right? Okay, now what? Well, now let's remember, right? Here, f of A is less than L. So I'm going to just write a little note here. F of A less than L, and f of B greater than L. So then you look at Z, and you ask yourself, well, what's the story with C? Is it less than L or greater than L, right? So here we go. If f of C is greater than or equal L, set A1 equals A, and B1 equals Z. And if it's the other way around, so if f of C is less than L, then set A1 equals C1 and B1 equals B. In other words, if f of C is greater than or equal L, then we're going to pick the left one. And if it is less than L, we're going to pick the right one. So if, how do I write this? Like this. So if f of C is greater than or equal L, pick this one. And if not, we do another picture. If f of C is less than L, then pick this one, right? And then set I1 to be A1, B1, and L1 to be the length of I1, which is just L over 2, right? The length is half of the previous length. Okay? And so do you see what we're doing now? So what happened now? Well, what happened is that we're going to go from, we're making our problem smaller, right? So before we were working with this big interval, A to B. And then what we're saying is pick the midpoint. And if the midpoint is, when we apply the function at the midpoint is greater than L, then now pick the left interval. If when you plug the midpoint and you get less than L, then pick the other interval. And look what properties of these intervals we have. We have the property that here is less, and this endpoint is less than L, and in this endpoint is greater than or equal L. And here in this endpoint is less than L, and in this one is greater than or equal L, right? So what is it that we're gonna do after this? Well, we're gonna keep doing this, right? So now work with these ones. either this or that. And then look at the midpoint and ask yourself the same question. What is f of that? And depending on what, if it's positive or negative, you pick one interval or the other interval, right? So let me do one more. So so now you consider, let's call this one C1, actually. So I'm gonna keep doing this. Now, so the next thing I will do here is consider Z2, which is going to be the half point between A1 and B1. And then I proceed the same way. If C2 is greater than or equal L, then I set A2 to be A1 and B1 to be Z2. And if the other thing happens, if it's less than L, then we say A2 to be C2 and B2 to be B1. Right? So depending on what whatever one we have, so we pick the one so that you have going from less than to greater than, right? So for example, if we were in this one, and so we pick this one is Z2, and it depends. If f of Z2 is less than L, then we're gonna pick this one. And if f of C2 is greater than or equal L, then we're gonna pick this one, the one on the left, right? That's what we're saying here. So what happens here is now that we set I2 to be A2, B2, and the length is now L over 4, right? I'm gonna write it as L over 2 squared. Okay, and we keep doing this. Is it clear? So every time you have the interval, the new one you get, you have it, and depending on the sign of when you apply the function on the midpoint, you either pick the right one or the left one, right? I think I have a mirror symmetry in my camera, so maybe doing left and right opposite. But you pick one of them, the one that has you going from less than to greater than, right? And it has to be like that, because one on the left endpoint is less than, on the right endpoint is greater than. So in the middle it's either going to be less or greater than, and you pick the one that is opposite. Okay, so in that way, so proceed recursively to get an interval AIN, which will be ANVN, with this property: f of AN is greater than or equal L, and f of BN is less than L, right? And the length of IN is L over 2 to the n. So every time we have, right? Okay, now what? Well, now we have a bunch of these intervals, and these intervals are nested, right? So we have I1, we have I0, that's the original one. Then I1 is inside, and I2 is inside, and I3 is inside, and so on. They're all inside. So we are going to use that nested interval property, remember? So note that I1 is a subset of I2. I should start with I0. They're nested like this, right? And they're all closed intervals. So by the nested interval property, the intersection is not empty. So by the nested interval property, the intersection is non-empty. So let's pick someone in the intersection. Let's call it X. All right. And what do we know about X? Well, it has to be like this, right? We have A less than or equal A1, less than or equal A2. So all the A's come first. Then there's X, and then all the B's come. Right? Because this guy is in the center of all the nested intervals. Right? What else do we know about the A's and the B's? Well, what is the distance from X to AN? How close are X and AN? Well, I don't know, but because X belongs to IN, then this is for sure smaller than BN minus AN, correct? So this is because X belongs to the interval IN. And these are the endpoints of the interval IN. So that's the longest you can be, right? The two farthest points in the interval IN are the endpoints from AN to BN. So, and this is the length of IN, which we know is L over 2 to the N, right? And the same happens for BN. So if you look at the distance from X to BN, the same happens. So the important thing to note here is that this goes to 0, right? So in the limit, when you can make this as smaller as you want because 2 to the N grows really, really fast. So this implies that the limit of AN equals the limit of BN equals X. So both endpoints approach X, right? And we're almost done. There's only one thing we haven't used at all in all of these properties. I don't know if you realize, we haven't used the function is continuous, right? We haven't used continuity of F yet. So now it's a moment to use the continuity of F. So if we know that these two sequences approach X, right, that means X is a limit point. And therefore, what happens when we apply the limit of the function of AN? So it follows that the limit of F of AN equals F of X. And that's the same of the limit. These two both, because these sequences approach X, then F of those sequences approaches F of X. So this is by continuity of F at X. So we finally use continuity, right? So this happens. Now we're also going to use continuity in a different way. Why? Because let's remember what we know about the AN and the BN. Let's go back a little bit here, right here at the top. You can see it right here. So we know that F of AN is greater than or equal L, and F of BN is less than L, right? I'm gonna write it here. You'll see it in just a moment. So in general, we know that L is less than F of AN. So L is sandwiched between F of BN and F of AN. Right? So we know this happens. So now we apply the squeeze theorem. So by the squeeze theorem, if I apply the limit, this should happen. But these two are F of X, right? So these two numbers are both F of X. That's what we did before. So these two numbers that are both equal to F of X sandwich L. That means L has to be F of X. And that is it, right? So therefore, f of x is L. And that's the number we were looking for, right? This is the number, the mysterious number C. So we just found out the number that is equal to L, right? And why do I like this proof? Because it sort of helps you find the C, right? It's kind of like the 20 question game, yes? So you're trying to guess a game, and I know that the first choice is too small, and the last number is too big. So then I ask you for the middle one, and you tell me, right, is it less than or greater than? And then depending on your answer, I go here or there, and I keep asking for the midpoint till I eventually capture the truth, right? It sort of follows that simple, very, very simple idea. Okay? All right, questions? Okay, now there is one last part that we see in this section, which is this. So right now we saw that if f is continuous, implies that f has the intermediate value property. What is the intermediate value property? It means that if you achieve one point and another point, then you achieve everything in between, right? The statement of the intermediate value theorem. So this means if f of A is less than L less than f of B, or f of B is less than L less than f of A, then there is C such that C between A and B such that f of C is F. That's the intermediate value property. So if f is continuous, then it implies this property. What about this question? Is it true that the opposite happens? Is it true that if you have a function that has the intermediate value property, then it's continuous, right? Oh, nice question, right? And it turns out that this property is false, right? So the converse is not true. And one simple example is, our old friend, the function sine 1 over x on the interval 0. So I want to close the interval. Hold on just a sec. Should I give you? Oh, okay, well, we'll modify our function a little bit. So this, if x is not 0, 0 if x is 0. And so this function is not continuous, right? F is not continuous at 0. We saw that already. It's not continuous at 0 because it oscillates like crazy. So we can find two sequences, one of them that is always 1, 1, 1, 1, and the other that's always -1, -1, -1, and both of them approach 0. So it's not continuous at 0. However, it does have the intermediate value property. However, f does have the intermediate value property. Of course, right? Because either it is continuous, so the only point where it is not continuous is near 0. So if you pick any interval that doesn't have 0, then it's gonna work by continuity. And if you pick 0, the thing is that near 0, it oscillates like crazy. So it takes near 0, it takes all the numbers between -1 and 1 arbitrarily many times. Yes, so this is such an example of a function where it's not continuous, but it does have the intermediate value property, right? You can also make it, if instead, you can use this same function with domains, say, from -1 to 1, right? So if you pick, as long as you have the point 0, it's gonna work as one of these examples. All right. So let me, I'm gonna stop right here. Let me just make sure that you guys don't have any questions.
I have a question just about exam.
Yes, go ahead.
So for the homework problems, this 5.2 and 5.3, although on the calendar it shows that we're going to cover 5.4. So I was wondering, does the exam cover 5.4 as well, or is it just 5.2 and 5.3 along with chapters 3 and 4?
Let me check my notes. I think our exam covers, not sure. Let me get back to you on that.
Okay.
Yeah, but we'll still have some time, right, for our exam? Yeah.
I was just kind of curious to see how many sections are covered.
Yeah, I will. So Jason asked, will the exam still be based off the homework problems from the section? The answer is yes. So essentially, if you do all the problems and all the homework problems, then you should be set. So usually I make them easier, right? I take some of the homework problems and I make them even more particular, right? More specific. If at all, or only as part of it, right? If it has multi-parts, then I usually pick some of them only. Okay, any other questions? All right. Enjoy your weekend, guys. I'll leave you, so I have another class to teach in about 10 minutes. All right. See you.
Thank you.